Welcome to the second part of Module 2. Let's get started. The 4 resolutions. One of the first considerations any user must make regarding remotely sensed data is its quality. For most scientific research, good quality data needs to contain information that is relevant to the scale and time period of the study, meaning that sensors are often designed for a specific application. The manner in which we describe a sensor is through 4 key resolutions. 1. Spatial resolution. Spatial resolution determines the usefulness of a dataset, representing the scale of information collection. It's defined as the ground area represented by a single pixel, the smallest digital element. Pixels represent mean values of reflected transmitted radiation over an area. The spatial resolution is affected by the sensor's field of view, FOV, angle of FOV, and sensor's distance from target. Larger pixels result in lower spatial resolution, while smaller pixels yield higher spatial resolution. When a sensor is in motion, the instantaneous field of view, IFOV, considers the FOV at the time each pixel was collected. Choosing the right spatial resolution involves balancing pixel size to observe features of interest, ensuring data storage and processing feasibility, and covering the entire study area. This balance influences research objectives and pixel size, ultimately directing the user to a specific sensor for their application. Spatial resolution is crucial in remote sensing, impacting dataset usefulness and sensor selection for various uses. Second, temporal resolution. Much like spatial resolution deals with the space that a sensor observes, temporal resolution refers to the time interval between successive observations of a given space. Temporal resolution can span seconds or years and is a requirement when investigating change. An acceptable temporal resolution is defined inherently by the nature of the study. For example, a study monitoring the annual urban expansion of Vancouver, BC, would have a temporal resolution of 1 year. Other common temporal resolutions include hourly, for applications monitoring weather, and daily, which is often used when monitoring plant phenology. The interval between successive observations is often called revisit time and is determined by the type of platform on which a sensor is deployed. Sensors that remain stationary can have revisit times measured in seconds, while sensors moving faster or slower than their target area can take multiple days before they observe a location again. Interestingly, sensors have been designed to be both stationary and mobile at a variety of spatial scales. Both airborne and spaceborne sensors have the capacity to remain stationary over a single location or travel faster than the Earth rotates and capture imagery over most of the Earth's surface in a matter of days. Third, spectral resolution. The term spectral resolution is often used to refer to any single component of its definition. In scientific literature, it is not uncommon to find spectral resolution referring to the number of spectral bands, discrete regions of the EMS, that are sensed as a single unit, the location of these units, or groups of bands, along the EMS, the number of individual bands within each unit. Each of these components plays a role in describing the spectral resolution of a pixel and enables users to identify appropriate sensors for their application. It is also important to consider the laws associated with the energy of EMR. Recall that shorter wavelengths have more energy, which makes it easier to detect. The implication of this is that longer wavelengths require larger bandwidths for the sensor to observe them. This is an important theory to note, as the consequences of a decrease in energy is a decrease in spatial resolution. A larger number of bands need to be combined to collect enough information. A common method for visualizing the spectral resolution of a sensor is to place each band along the EMS according to its associated bandwidth and wavelengths. This allows users to determine which sensor best captures the information they are interested in studying. For some applications, such as land cover, it is acceptable to use sensors with relatively wide bands collecting information in a small number of strategic locations along the EMS. For other applications, spectral information may need to be more detailed and capture information using thin, adjacent bands spanning a large region of the EMS. The figure shows the locations of bands for various sensors deployed by NASA on one or more Landsat missions. Fourth, radiometric resolution. Radiometric resolution is the quantification of a sensor's ability to detect differences in energy. Photons enter a sensor through a filter that only permits specific wavelengths. The energy of the photon is recorded as a digital number dn, and the digital number is assigned to a pixel. A simple visualization of radiometric resolution would be to think of 3 colors: red, green, and blue. A sensor detecting energy in the ranges of these three wavelengths would contain three separate detectors. Each detector is specialized to record energy in a single unique range, say red tilde 700 nanometers. The amount of energy that is recorded while observing an area is stored in a pixel as a DN, with the lowest DN number representing zero sensor-detected energy in this wavelength range, and the highest DN representing maximum sensor-detected energy. The radiometric resolution of a detector, then, is the number of discernible values, or segments, present between 0 and maximum DN values. These segments are usually referred to as bits and can be mathematically represented as an exponent of 2, equation 2.3. The number of bits that a detector can resolve may also be called the color depth of the image. Figure 7 clearly presents the increase in detail provided by additional bits, but recall that increasing any resolution generally increases storage and processing time. As such, it is important to select an appropriate radiometric resolution based on the needs of your study. Equation 2.3, 8 bits equals 28 equals 256 levels. Types of sensors. Sensors are the key component of remote sensing systems, as they are responsible for collecting the data that is used to create images and other forms of information. There are many different types of sensors used in remote sensing, each with their own unique characteristics and capabilities. 1. Optical imaging sensors. Optical imaging sensors operate in the visible and reflective infrared ranges. Typical optical imaging systems on space platforms include panchromatic systems, multispectral systems, and hyperspectral systems. In a panchromatic system, the sensor is a monospectral channel detector that is sensitive to radiation within a broad wavelength range. The image is black and white or grayscale. A multispectral sensor is a multi-channel detector with a few spectral bands. A hyperspectral sensor collects and processes information from 10 to 100 of spectral bands. A hyperspectral image consists of a set of images. Second, thermal IR imaging sensors. It operates in the electromagnetic spectrum between the mid to far infrared and microwave ranges, roughly between 9 and 14 micrometers. Any object with a temperature above 0 can emit infrared radiation and produce a thermal image. A warm object emits more thermal energy than a cooler object. Therefore, the object becomes more visible in an image. This is especially useful in tracking a living creature, including animals and the human body, and detecting volcanoes and forest fires. 3. Radar imaging sensors. A radar, microwave. Imaging sensor is usually an active sensor, operating in an electromagnetic spectrum range of 1 millimeter to 1 meter. The sensor transmits lights to the ground, and the energy is reflected from the target to the radar antenna to produce an image at microwave wavelengths. Unlike infrared data that help us identify different minerals and vegetation types from reflected sunlight, radar only shows the difference in the surface roughness and geometry and the moisture content of the ground. Remote sensing in agriculture. Agriculture provides raw materials, fuel, fibers, and food to humanity. This role needs to be fulfilled within climate change and environmental sustainability, combined with the expanding population while maintaining agricultural activities' viability to sustain livelihoods. The application of remote sensing in agriculture can help the evolution of agricultural practices face different types of challenges by providing information related to crop status at different scales all through the season. When electromagnetic energy hits the plants during hyperspectral remote sensing in agriculture, one of three things can occur. The energy will be reflected, absorbed, or transmitted, depending on the wavelength of the energy and the characteristics of the plant itself. The reflected, absorbed, and transmitted energy can be detected by remote sensing technology. The relationship between the three occurrences determines the spectral signature of the plants. This signature is unique to different plant species. During the last 2 decades, remote sensing techniques have been applied to explore agricultural applications such as crop discrimination, crop acreage estimation, crop condition assessment, soil moisture estimation, yield estimation, precision agriculture, soil survey, agriculture water management, agro-meteorological, and agro-advisories. This brings us to the end of the second part of this module. Stay tuned for the last part.